Welcome. Today, we are exploring a very important change in JavaScript, multi-threading. For a long time, JavaScript meant single-threaded work, but that has changed quite a lot.
This session, generated by AI, looks at how JavaScript uses multiple threads now, both in web browsers and on servers.
Our goal is to give you clear, useful knowledge. We want you to understand why and how to build faster applications using these new ideas.
Exactly. We will explain the main concepts, we will clear up some common misunderstandings, and we will show you how to use these tools correctly.
By the end, you should have a solid grasp of multi-threaded JavaScript, a good base for your work.
So let's begin by asking, why multi-threaded JavaScript? Why talk about this now? Most of us learn JavaScript as, well, single-threaded.
That's true, but modern applications need more, especially those doing heavy calculations. The old way isn't always enough.
And it's interesting how that single-threaded idea leads to confusion. Take promises, for instance. Many think they run code at the same time in parallel.
But they don't, do they?
No. They are great for handling tasks without blocking the main thread. But the tasks still run one after another on that single thread. This difference is very important.
Especially if you have experience with languages like C++ or Java, where threads work differently. The main point is, asynchronous is not the same as parallel.
Correct. So who really needs this knowledge? We're thinking mainly of engineers who know JavaScript well but maybe haven't used multi-threading much before.
We will cover the basic ideas, but also more advanced ways to use threads. It should be a complete picture.
And when you build these applications, you usually find two main ways: using message passing or using shared memory. We need to understand when to use each one.
Okay, let's cover the basics first. Threads and multitasking. Computers used to run just one program at a time. Simple days.
Then came multitasking. Computers started running many programs, switching between them. Early systems used cooperative multitasking. Programs had to agree to take turns.
Which could cause problems if one program didn't cooperate correctly.
Yes. Modern systems use preemptive multitasking. The operating system decides when programs run. It's much smoother.
And this brings us to processes and threads. When you start an application like Node.js, that's a process. It has its own memory.
A thread is smaller, it runs inside a process, and crucially, threads within the same process share memory.
This shared memory makes sharing data fast, but it also makes things more complex, doesn't it? You have to be careful.
Very careful. Historically, JavaScript mostly used just one thread. We used callbacks or async await to handle many tasks.
These patterns made applications feel responsive, but they didn't use multiple CPU cores at the same time. Tasks ran one after the other.
But now things are different. Modern JavaScript environments support threads. And if your computer has multiple CPU cores, these JavaScript threads can run tasks truly at the same time.
This is a big change for performance, which leads to concurrency versus parallelism, a key difference.
It is. Concurrency means managing multiple tasks in overlapping time, like one cook handling several dishes, switching quickly.
Parallelism means tasks run at the exact same moment, like having many cooks, each working on a different dish simultaneously.
And the important point for you is, threads do not automatically give you parallelism. You need multiple CPU cores for that.
So you always need to measure. Check if using threads actually makes your application faster. Sometimes it might just add complexity.
That's right. And another interesting thing, even when you think your JavaScript program is single-threaded, it's often using multiple threads already.
How so?
Well, the V8 engine, for example, uses background threads for things like garbage collection, cleaning up memory.
And Node.js uses a library called Lubov. It has a pool of worker threads, usually 4 by default, for slow tasks like reading files from disk.
Browsers also use threads for many things, like drawing the user interface you see on the screen.
So the lesson here is, don't assume your app uses only one thread. These background threads are always there. They use memory and CPU power too.
Now, let's look at browsers specifically. Chapter 2 in the source material covers web workers. Browsers use different JavaScript engines, but they all provide ways to use threads.
Dedicated workers are the most common type, maybe the simplest. What's their main job?
Their main purpose is to run JavaScript in a separate thread, away from the main browser thread that handles the user interface.
This keeps the UI smooth, right? So if you have a long calculation, it doesn't freeze the page.
Exactly. Communication happens through message passing. You send data to the worker, and it sends results back. It's all asynchronous.
The Hello World example shows this well. You create a worker, use postMessage to send data, and onMessage to receive the reply.
But there are limits. Workers cannot directly change the web page, the DOM, and they usually need to be loaded from a web server, not just a local file.
Then we have shared workers. How are they different?
Shared workers allow multiple browser windows or tabs from the same website origin to use the same worker thread.
Ah, so it can hold shared information, shared state, even if one window closes.
Precisely. Communication uses a special .port object. But be aware, browser support varies. Safari, for instance, doesn't fully support them currently. Debugging can also be a bit harder.
And the state disappears only when all connected windows are gone. Managing those connections sounds important.
It is, to prevent memory leaks. Then there are service workers. They act like a proxy, sitting between the web pages and the network server.
They can run even when the website isn't open. That's useful for offline features.
Yes, perfect for caching files and managing network requests, making sites work offline. But again, they have limits. No DOM access, no blocking network calls, and they require HTTPS for security.
So their main job isn't heavy computation, it's more about network control and caching.
Oh.
You'd use other workers for pure multi-threading tasks.
Correct. And service workers should be an enhancement. Your website should still work without them.
Are there other ways for different browser parts to talk? Like iframes?
Yes, parent windows and iframes or pop-ups can use post message. And there's also broadcast channel.
What does broadcast channel do?
It lets many windows, iframes, and even workers from the same origin send messages to a shared channel, like a public announcement system. Very flexible.
Sending simple messages is fine, but for complex apps, you need better patterns, like RPC, remote procedure call.
RPC makes talking to a worker feel like calling a function directly. You send a request, like a function name and arguments, and get a response back. An ID helps match requests and responses.
And the command dispatcher pattern helps the worker figure out what to do with the request.
Exactly. It maps the command name in the message to the actual function code inside the worker, and it should handle commands it doesn't recognize.
Combining RPC and command dispatcher gives you a nice RPC worker. It hides the messaging details, making worker code look more like standard asynchronous functions.
Now shifting to Node.js, Chapter 3 covers worker threads. Node.js is huge for servers and build tools, often doing heavy processing. Good candidates for parallelism.
Before worker threads, how did Node.js use multiple CPU cores?
Mostly by using separate processes. The cluster module was common for web servers, spreading requests across multiple worker processes.
But processes don't share memory easily, unlike threads, so sending data between them is slower.
That's the key difference. Now, Node.js has built-in threads with the worker threads module. It's similar to browser web workers, but not identical.
What are some differences?
Well, in a worker thread, process.exit only stops that thread, not the whole application. Some process functions aren't available, like changing the directory. And signal handling with process.on is different.
Anything else to watch out for?
Node.js worker threads share the same Labouv thread pool for I/O. So if you do lots of file reading, just adding workers might not help unless you increase the UV thread pool size.
You can also send initial data to a worker when you create it using worker data. That data gets copied, though.
Let's think about that happy coin example again, finding special random numbers. Using worker threads, you can split that search across multiple threads and find the coins much faster.
But managing lots of workers yourself can be tricky. Are there tools to help?
Yes, libraries like Pacina provide worker pools. It manages a set of workers and a queue for tasks. You just call .run to submit a task and get a promise back.
Sounds convenient. Is there a catch?
There can be. If you send tasks too quickly, the queue can grow very large and use up all your memory.
How do you prevent that?
You can set a limit on the queue size using max queue, maybe set to auto. Then you wait for the drain event, which signals the queue has space, before adding more tasks.
That makes sense. And performance, is it always faster?
Not always. For very, very small tasks, the time spent sending messages back and forth between threads can actually be more than just doing the work in one thread.
Okay, let's move beyond message passing. Chapter 4 discusses shared memory. Why use this?
Message passing is safe, but can be slow because data needs to be copied or serialized. Shared memory lets different threads access the exact same data directly, like in C or C++-ish.
What tools does JavaScript provide for this?
The main tools are shared array buffer and atomics. They are very powerful for performance, but also dangerous if not used correctly.
Why dangerous?
Because if multiple threads change the shared data at the same time without coordination, you get race conditions. These are bugs where the result depends on the exact timing, making them very hard to find and fix.
Let's break down shared array buffer. It's a block of memory for binary data, right? Fixed size.
Yes, and unlike a regular array buffer, it can be shared between threads. Data is stored as raw bytes, often shown in hexadecimal.
But you don't work with the raw bytes directly, you use views.
Correct. You use type-to-array views like uint8 array for unsigned 8-bit integers, or in32 array for 32-bit signed integers, or float64 array for standard JavaScript numbers. These views tell JavaScript how to interpret the bytes as numbers.
And writing numbers involves conversion.
Yes. If you write a JavaScript number into, say, a uint8 array, it gets converted to an 8-bit integer. Large numbers might wrap around. You need to be aware of the view's type.
So how do we use this shared memory safely? That's where atomics comes in.
Exactly. Atomics provides special functions that guarantee atomic operations. An atomic operation happens completely or not at all. No other thread can interfere in the middle.
This prevents race conditions for simple operations.
Yes. Functions like atomics.add, atomics.store, atomics.load, and atomics.compareExchange are crucial.
Explain atomics.compareExchange again.
It checks if the value at a specific memory location is what you expect it to be. If it is, it changes the value to a new one, all in one atomic step. This stops threads from overwriting each other's changes based on OIL information.
These atomic operations help create critical sections, parts of code only one thread should run at a time.
Precisely. One small detail. Atomics methods usually return the value you tried to write, not necessarily the final value after it fits into the type array's format. So always write values that fit.
What about storing more complex things than numbers in these buffers, like text or objects?
For Booleans, you can pack 8 into a single byte. Strings are trickier. Basic characters might fit 1 byte, but others need more. Text encoder and text decoder handle UTF-8 encoding safely.
And objects.
You can turn them into JSON strings and encode that.
Right.
But for performance, it's often better to just pass simpler data or use the structured clone algorithm if you don't need the exact same object instance shared.
Chapter 5 goes deeper into coordinating threads using shared memory. Basic atomics aren't always enough.
Sometimes threads need to wait for each other. Atomics provides methods for this, similar to Futex in Linux. They work mainly with in32 array and bigint64 array.
What are these methods?
The main one is atomics.wait. It makes the current thread pause or freeze at a specific memory location until another thread calls atomics.notify on that same location, or a timeout occurs.
Is there a catch with atomics.wait?
A big one. Browsers do not allow atomics.wait on the main UI thread because it would freeze the entire page. Node.js does allow it.
So atomics.notify is used to wake up a waiting thread.
Yes. You can tell it how many threads to wake up. There's also atomics.waitAsync, a newer version that uses promises and doesn't block the thread, but it has some performance cost.
Timing seems tricky here. You mentioned non-determinism.
Yes. Threads waiting first are usually woken up first, but you cannot absolutely rely on that order. Debugging based on log message order can be misleading.
So your program needs to work correctly no matter the exact wake-up order. How do you know when a worker thread is even ready to start using shared memory?
A common, reliable way is for the worker to simply send a post message back to the main thread once it's done its setup. This works because message passing is slower than the synchronous setup code.
The book uses Conway's Game of Life as an example. How does that fit?
It's a grid simulation where cells change based on neighbors. Perfect for showing threads working together on shared data. The grid's stored in a shared array buffer. Atomics.wait and coordinate the updates between calculation steps.
And the advice is to keep atomics.wait off the main thread.
Definitely. Design your application so some threads focus on CPU-heavy atomics work while others handle UI events or I/O. You can use bridge threads to wait on results and pass them back via messages.
Great. Let's talk patterns in Chapter 6. These build on the basic atomics and shared array buffer.
The thread pool is a classic, a group of workers ready for similar CPU-heavy tasks. Node.js's libmove uses one internally.
How many threads should be in the pool?
Often, it matches the number of CPU cores. But remember, your main thread and other background tasks also use cores. You really need to test and measure for your specific application.
How are tasks given to workers in the pool?
Different strategies exist. Round robin just cycles through workers. Random picks one randomly. Least busy gives the task to the worker with the fewest current tasks.
Another key pattern is the mutex, a lock.
Yes, a mutex, for mutual exclusion. Atomics operations are small. A mutex protects a larger block of code, a critical section, ensuring only one thread can execute it at a time.
This prevents race conditions for more complex operations involving multiple steps.
Exactly. You can build a mutex using atomics.wait, notify, and compare exchange. It's fundamental for many shared memory tasks.
What about streaming data between threads? The book mentions ring buffers.
A ring buffer, or circular buffer, is an efficient way to pass data. It's a fixed-size array acting like a queue. Head and tail pointers move around, wrapping from end to start. Data isn't moved, just the pointers.
How do you make that safe for multiple threads?
You need a mutex to protect access to the head, tail, and length indicators when threads read or write. This prevents one thread from interfering with another's operation on the buffer.
So a shared ring buffer would use a mutex internally. Makes sense. Finally, the actor model. How is that different?
Very different. Actors are independent units. They communicate only through messages. They do not share memory at all.
What's the benefit of that?
It completely avoids race conditions and deadlocks by design. Each actor processes messages one by one from its own queue.
How do you implement actors in JavaScript?
You can simulate them using Node.js processes or worker threads, sending messages between them, maybe using JSON.
A key advantage mentioned is hot code loading.
Yes. Because actors are isolated, you can potentially update parts of your application by launching new actors with new code and phasing out the old ones, all without stopping the system. Messages might not arrive in order, though.
Chapter 7 touches on WebAssembly or WASM. What's its role in multithreading?
WASM is a fast binary format for code. Languages like C++, Rust compile to it. WASM itself has instructions for atomic operations, much like JavaScript's atomics.
So WASM-con can also use shared array buffer.
Yes. If a WASM module's memory is a shared buffer, then multiple threads, web workers or worker threads, running instances of that module can share that memory and use WASM's atomic instructions to coordinate.
Can you compile existing threaded code from other languages?
Often, yes. Tools like mscripton for C++ can compile code using POSIX threads into WASM that uses workers. Rust has similar capabilities. AssemblyScript, which compiles TypeScript-like code, also supports atomics for WASM. You manage the threads from JavaScript.
Finally, Chapter 8 asks the big question. When should you actually use multithreading?
The main reason is performance. But threads add complexity. Always follow the KISS principle. Keep it simple. Only use threads if they genuinely solve a performance bottleneck for your problem.
Memory usage is also a factor?
Absolutely. Each worker uses extra RAM, around 6 MB in Node.js perhaps. You need to account for that.
And what about systems with few CPU cores?
On a machine with only 1 or 2 cores, threads might actually slow things down. They compete for the same core, and the system spends extra time switching between them and managing messages.
So performance on your powerful development machine might not reflect performance on a smaller server. Always test in the real environment.
Crucial advice. For Node.js servers, sometimes scaling horizontally running multiple copies of your app in containers is simpler and more effective than building one complex multi-threaded process.
When is multi-threading a really good fit then?
Definitely for CPU-heavy tasks, complex math, image-video processing, also for problems that can be easily divided, like in MapReduce patterns used in search or databases. Server-side template rendering can also benefit.
The general idea is problems that don't need much shared data or where sharing is simple are easier to parallelize.
That's a good rule of thumb. Let's quickly recap the challenges, the caveats.
Shared memory is complex. JavaScript objects aren't truly shared. They're copied or data is extracted.
Web workers can't access the DOM. Some browser APIs don't work or work differently in workers. The structured clone algorithm has limits.
Browsers need special security headers, CUPs, COEP, to enable shared array buffer. And knowing exactly when a worker is ready for shared memory requires custom solutions.
So you should now have a better picture of multi-threading in JavaScript for both browsers and Node.js. They are powerful tools for speed, but bring complexity. Measurement is key.
To really get a handle on these tools and see more examples, we strongly recommend reading the full book. It provides much more detail.
It really digs into practical examples that will help you build solid multi-threaded applications.
So here's something to think about. When does the performance gain from using threads justify the extra development effort and complexity? How can you apply these ideas thoughtfully in your own projects?
This review was generated by AI.